So I'll send out an email to remind everybody when our final exam is. But remember, it is open note, open book, so you're not just limited to one page for this one. That's because it's a common final, and that's the easiest way to rectify it. However, I feel like I should mention that, you should still do the whole cheat sheet thing, because digging through your notes during the exam is not going to be great. So we're going to go over the Harvard practice final for data structures because I really like it. And then if we have time remaining, we're going to go and tackle another one. I like this one because it's multiple choice, and a lot of the answers we get to think about why they're wrong. So you can identify some things that are going on with them. All right. So also, when I need to remember to do this for stuff that's multiple choice, that says, hey, if you're not sure, you can label something as a second choice and get 1 point if your second choice is correct, but your first was wrong. Anyway, so let's go ahead and get started. So suppose items A, B, C, D, and E are pushed in that order onto an initially empty stack. Stack S is then popped 4 times. As each item is popped off, it's inserted into a queue. 2 items are removed from the queue. What is the next item that will be removed from the queue? Now, if you're trying to do that in your head and you're not able to do it, don't worry, neither am I. So that's because with these kind of questions, you should not do them in your head. You should totally use any kind of writing you have in your disposal. So A, B, C, D, and E are each inserted into an initially empty stack. Okay? S is then popped 4 times. As each item is popped off, it's inserted into an initially empty queue. So I'll just simply put front over here and an arrow to indicate that that's the front of the queue. So E gets popped off, then D, then C, then B. Right? So we pop 4 times there. And now, what is the next item that will be removed from the queue? That item is, then we remove 2 items from the queue. So we remove from the front of the queue. So you remove E, then D. So what is the next item that's going to come off the queue? C, right? Fairly straightforward. All right. So let's go ahead and take a look at this one. If the binary tree below is printed by a pre-order traversal, what would the result be? And I just gotta say, I think my trees are much prettier than the trees they had. But I mean, I used latex, so of course they are. So what would the result be if we did a pre-order traversal? So pre-order means that we do the root first. So anything that starts with 9 is clearly wrong. So that means that the answer has to be something that starts with 6. Now, C goes 6, 9, and I have no idea what that's doing over there. So obviously that's wrong. So the choice has to be D or E. So that's pretty good. So pre-order would mean 6, 17, 9 next, because we would go 6, 17, 9, then 4, then 22, then 16, then 12, right? We do myself, then I do my left, then I do my right, and that's recursively done. So it would be D. Now E goes, if we notice, 6, 17, 22, 9, 4, 16, 12, which is a level order traversal, which we'll get into a bit more detail. All right. I like this one because I should totally steal it at some point. I'm not going to for this exam, but I should totally steal it. A graph implementation that uses a 2-dimensional array to represent the edges would be most reasonable for which of the following cases? So, right, we hopefully learned that, you hopefully learned that there are 2 ways you can represent a graph, right? What are the 2 ways you can represent a graph? Right, what are the 2 ways you can implement a graph? Not tree. Adjacency list, right? And then, an adjacency matrix. So using linked lists or using a 2D array, right? If we use a linked list, basically each node, we have a list of linked lists, right? Where each node basically has a list of, or it's actually better to put it as to refer to it as a map, where basically the key is the node and the value is all the nodes it shares an edge with. Right, a linked list of all the nodes it shares an edge with. Now, this is good if you've got a short amount, if you have a small amount of edges, because you only store edge information for what you need. But if you're a graph with a lot of edges, then guess what? You're storing a lot of information for each possible. You have to iterate through a lot of edges to find the particular edge you're looking for. So we've learned that adjacency lists are good for what we call sparse graphs. Adjacency matrices are good for dense graphs, where basically we have a 2D array for all possible combinations of edges, right? Basically, so each entry has a potential edge to store there. We leave it null if there's nothing there. Otherwise, we have the edge information, right? Which might be 1, or if we're just putting in costs, it could be 1 and then positive infinity if we don't have an edge, right? But overall, the point is that if you don't have a if you don't have a lot of edges, if you're in a sparse graph, then an adjacency matrix will be, say you have 1,000,000 nodes but only 2 edges, right? Well, we're storing information on 2 edges, but we need to store information. But an adjacency matrix would be 1,000,000 by 1,000,000, which is way too much. So, yeah. So that would be a waste of information. Linked list would do that much more efficiently. So we use adjacency lists for sparse graphs and adjacency matrices for dense graphs. And dense graphs, we typically say the cutoff point between sparse and dense is if 25% of all possible edges exist. Then it's dense, right? So in other words, if you've got, say, 1,000 nodes, then 1,000 times 1,000 is what? 1,000,000, right? So you want 25% of 1,000,000 in that case, edges before you use a matrix. So let's look through this. So it's looking for when would we use an adjacency matrix? So 1,000 nodes versus 12,000 edges, that's a sparse graph, right? There's relatively the same amount of nodes as there are edges. Whereas answer B, where we have 100 nodes and 4,000 edges, well, 100 squared is 10,000, right? So that's kind of the same magnitude as 4,000 there, right? That's 40% of all possible edges. So we'd want to use this two-dimensional array for B. Let's just check the other examples. 1,000 nodes, 10,000 edges, right? That seems like a lot more edges, but 1,000 times 1,000 is 1,000,000, and 10,000 is actually a very small percentage of 1,000,000. 10 nodes, 20 out of 100 possible edges. So only 20% are used. So a bit more of a toss-up there, but still would lean towards being a sparse graph. And obviously, since E is wrong, since we know we can represent stuff with a array. All right. Now it says, assume we've got a binary search tree. I like this question a lot. A binary tree is constructed of nodes that are instances of the following class, right? They don't use generics, so point for us because we use them. So we've got, these are values they're nodes that store a value and they have a left and right? So these are tree nodes. Consider the following method, right? So public static node mystery node root. So given a root of a tree, if root.right is equal null, return root. Otherwise, return mystery root.right. So I'll go back into what this does. You consult 3 supposedly tech-savvy consultants, and you get the following 3 opinions about what this method does when passed a reference to the root node of a binary tree. Consultant 1 says it will return the last node visited by an in-order traversal. Consultant 2 says it will return the last node visited by post-order traversal. And consultant 3 says it will return the last node visited by a level order traversal. Okay. So we'll go and tackle these each at a time to see which of these guys are correct. So which of these opinions is correct regardless of the contents of the tree? In other words, which guy is always correct? So what does this node do? So we pass it a root, and we say if we have a if we don't have a right child, we return ourselves. Otherwise, we return calling this on our right child. So this is going to continuously call the rightmost child until it gets to the rightmost child of the whole tree. Now, with this insight, we know that since this will get the rightmost child. We know that rightmost child. We know, as a matter of fact, that that's going to be the biggest thing in the tree, no matter what. The biggest thing in the tree. So that's got to be node. So consultant 1 has got to be correct, because in in-order traversal, the last node in an in-order traversal is the biggest thing. Okay. Furthermore, what about 2? We should probably come up with some maybe counterexamples. Assuming, we actually have ink. Okay. So, for counterexample for 2, a last node visited by a post-order traversal, that's fairly straightforward. Here's the counterexample. The last node visited by a post-order traversal is myself, right? I process myself. So it would go this left subtree first, then my right subtree, then it would be myself. So it can't be 2, right? It would be 2 in this case only, where basically I only have a left subtree. Now, level order traversal, since we haven't really gone over that one, that's actually equivalent to breadth first search, actually. Basically, what a level order traversal says is, right, I'm going to go and do this. A, B, C, D, E, F, G. So level order traversal would go A, B, C, D, E, F, G. And if you notice, that's actually breadth first search on a tree. If we treated this as a graph, it would be A first, then visit B, then visit C, then visit B's neighbors, then visit C's neighbors, and then visit D's neighbors, and then E's neighbors, and then F's neighbors, and then G's neighbors, right? It's just breadth first search, right? So the question is it always going to visit that last one, that last node? And the answer is it always going to visit the biggest node last? And the answer is no, and it might be tricky to find a counterexample. Let's see. It's going to visit the last node visited by a level order traversal. So, yep, I could. I was just double checking that answer. If we erase G, the last node visited by a level order traversal is F, which is not the biggest thing in the tree. So only 1 is correct. One only is correct. So, better get your money back from the other 2 consultants, because, or at least in regards to the tree stuff. All right. When you have a poorly chosen hash function, it's possible to have a situation in which the search time for a hash table of n items goes to what? What's the worst case scenario for a hash table when you're searching? O of n, right? Where basically we have these many items in the table, and you've got that many collisions. All right. I don't really see a need to go over this one. This one was on your first exam, and pretty much everybody got it right, which is how do you go through. All right. I like this one a lot because we got to think about the various data structures we use. Also, people did very, very well on the first page of exam 2. We're asking which data structure to use. There will be another one like that on the exam. And the Magic the Gathering question that was question number 4, that's actually true. The thing that is used, the game mechanic that is used to resolve spells in the order in the correct order is called the stack. So when you cast spells, they go on the stack. It is a literal first in, last out. So a police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so that it can be determined very quickly whether or not a given license plate is in the database.
speed of the response is very important. Efficient use of memory is also important, but not as important
as the speed. So that's worthwhile to note. Efficient memory is important, but we can't just say, I don't care about memory at all. We want to care about memory some. Okay, so which of the following data structures would be most appropriate for this task? A sorted linked list, a sorted array, hash tables with 1,800 entries, 3,600 entries, or 10,000 entries. Okay, so a sorted linked list is terrible. Terrible, terrible, terrible for this because it takes O of n time to search for a sorted linked list. You can't do binary search on a sorted linked list in a reasonable amount of time because it's just because you have to iterate to the middle point each time. It would be quite terrible. Be nice and memory efficient though, relatively, but not as memory efficient as a sorted array with 1,800 entries. This is the most efficient one because of course arrays are super efficient in terms of memory. Or rather, it's the most efficient in terms of memory. What's the speed of searching for something in a sorted array? Log n to do binary search. So that's pretty good. I mean, if we really cared about like having a small memory thing, if you care about small memory and you're keeping sorted data, use a sorted array. And if for some reason you need to keep it sorted, then this is your guy. But that's not a requirement. So let's take a look at the hash table. Now, a hash table using open addressing with 1,800 entries. That means that we have 1,800 entries, we have 1,800 parking spaces, and 1,800 cars. How long will it take to find a parking space? Freaking forever. In other words, what we're saying here is that basically it's gotten, or better yet, let's just think of that last car that we're trying to park in a parking garage, right? 1,799 spaces of the 1,800 have been filled. We're going to put in our 1,800th car, right? It takes forever to find the last parking space. In other words, when we try to insert this item, there's going to be so many collisions, a ridiculous amount of collisions. The more items you add to a hash table, the fuller it gets, the more collisions you're going to get, and the more the runtime approaches O of n. You never want your hash table to be filled up. So this would not be very memory efficient. This would take a long time, and while it would be more memory efficient than these, it would be just as memory efficient as the sorted array, but we don't even bother keeping things in order. And it might be slower than log n, so why use it? On the other hand, 3,600 entries is kind of that happy medium. Basically, we've got half the spaces are left unfilled, which means that basically we can, according to the formula we saw earlier, which you do not have to memorize, but the one that Knuth came up with. Do people know who Donald Knuth is, by the way? Because I need to go on a side if you don't. So Knuth is, there are many people who have I'm not sure what the Bible of computer science would be, right? The thing that everybody, at least owns and makes some effort to read. I don't know what that is. Knuth did not write the Bible. What he wrote was the Vatican Archives of Computer Science, because nobody's ever read that, but everybody's really happy that it's there. He's in charge of writing The Art of Computer Programming, which is huge. And the first 2 volumes of 4B are scheduled to be published 2019. It's been ongoing he's been publishing volumes of it since 1968. It's been a while. But it is the work. He's very, very well known. He's a very famous computer scientist. He does, but anyway, so he was publishing this book, and the typesetters abandoned monotype in favor of photosetting, and he became very frustrated in the inability to, put down his mathematical symbols in the way he wanted. So he took the time out to say, fine, you won't typeset my work. I'm going to create a language that will allow me to typeset my work. So we created TeX and Metafont, which then evolved into LaTeX. So TeX is great for that. So basically, if you notice how basically all your mathematical exams, and my exams actually, are written in this weird font that looks vaguely familiar, but you don't know where from, but everybody's using it. It's because they're probably written in LaTeX and used in tech, because these things are really good at producing mathematical formula. And for like forever, it was the only choice, because if you did it in Word, it would look ugly. Word's much better about that now. But yeah. Oh, and Metafont, how you can make various glyphs. So here, like, you can define this, and this will yield the following glyph for you. So you can define. So I have a feeling Tolkien would have loved this, because you could have totally made your own typeset alphabet. Anyway, yeah. So the volumes he's got a bunch of volumes for this on different stuff. Like volume 3 is just on searching and sorting, but he's very famous in that regard for that stuff. He also has a very interesting way of numbering his stuff. So the most recent version of Tech, which was released 5 years ago, is version 3.14159.265. Rather than incrementing the version number like the 3 or 4, he just adds another digit of pi every time he does a stable release. He also is known for, basically, if you find a typo, he'll give you, he'll send out a check to you for, reward check for $2.56, or a hexadecimal dollar. And I don't think many people actually end up cashing those. Although there his routing information is, so I don't know. That's not the greatest. There's that. Anyway, back to this. He came up with that formula because, of course he did. So on average, it will take about 2.5 searches to find, the item you're looking for. 2.5 spots. And what's log base 2 of 1800? Let's see. So we could split it in half to 900. Then we can split it in half to 4,500. We can split that in half to 225. And that in half, let's go ahead and just round down to 224 and say 112. And we're already well above the average time, right? That's already 4 checks that we need. So we want to do, we want to use scenario D. Scenario E, no. Even though it would run faster, it would not run noticeably faster, and we'd just be burning way more memory. So now let's take a look at this one. This one's a Huffman tree question. A Huffman tree is, and by the way, if you got the Huffman tree question wrong on exam 2, be sure to review it, because same kind of question is going to be on the exam, guaranteed. A Huffman tree is constructed for a text document containing 5 characters. The character E appears the most frequent in that text document, and the character I has the next highest frequency. Which of the following could be a Huffman tree for this document? So let's take a look. First off, can 1 be a Huffman tree for this document? No. What's wrong with number 1? Yeah, the T is in the, yeah. For the symbols have to be in the leaves for a Huffman tree. Okay, so for number 2, it says that the character E appears most frequently and the character I has the next highest frequency. Could this possibly be that? Well, E is the most frequent up here, so that works out. It has the highest way. I is tied with S, or at least it's on the same level as S-O-T. So maybe if this was like 1, 1, so if this was like 1, 1, 1, 5, a million, right? Then this could feasibly be that. Or 1, 1, 1, 2, that might be that, right? It could there's a way for this to feasibly work out that this is the next highest one, okay? Or it could be something like 10, 10, 10, actually, it would be like 10, 10, 10, 11 would probably be, yeah, that. So it's possible for that one. What about E? E and I are on the bottom level, which means that they would have the least frequent characters, therefore the most bits. So 3 and 1. So I'd have to say 2. And then I'd have to say none of these as my second choice, just in case I'm wrong about how to construct this, but I'm pretty sure I'm right. All right.
An array of 7 integers is being sorted by the heap sort algorithm. After the initial phase of the algorithm, which is constructing the heap,
so before we start sorting it, right? We've taken an array, we turn it into a heap. Which is a possible ordering for the array, right? Heapify, the first step in heap sort, turns an array into a max heap. So that means that each item in the tree needs to be each item in the heap needs to be bigger than its 2 children. So 85. Its children are 78 and 45. 85 is the biggest item in the array, right, if we just take a quick glance. So we can immediately rule out D because it is not a max heap. Awesome. So let's go ahead and see. 85 is bigger than 78 and 45, and we have to make sure this is a recursive process. So this compares 78 to its children, right? So this is the first item, this is the next level, and then this is the next level. So 78's children is big, so 78 is bigger than both its children, but 45 is smaller than both its children. So A is wrong, right? If I were to draw this for everybody, that first one, right? And you could draw this if you need to. That's actually probably a smarter way to do it, but I'm lazy, which is an excuse I use a lot. 51, 53, 47, and 49, right? I just simply went across. Right, this is essentially breadth first order, or breadth first search, or level traversal order. So 45 is is smaller than 47 and 49, so this is wrong. What about this one? 85, 49, 78, all right, 45, 47, 51, 53. Did I do it right? Does that look right? It's bigger than these. Okay, that's a strong contender there, because it looks correct. Okay. What about C? Is there anything I can do to immediately rule out C? 49 is smaller than its children, and what about E? 51 is smaller than one of its children, specifically 53. So B is the only correct one, right? I'm always tenacious. I always check. I'm like, wait a second. I'm going in order. Did I really find the right one on the second try, right? So, All right. This is also a fun way to do a tree question, and I'll probably subject our students to that when I teach it next time. Don't know when that is, though, because I've been shuffled off to 1051. So... All right, the binary search tree is below is constructed by inserting a sequence of items into an empty tree.
So we've got this tree. Which of the items will not produce this tree? So which of the following input sequences will not produce this binary search tree?
So in other words, which of the, right, 4 of these will produce, if we add all the items in order for A and then all the items for order in B and then C, one of these will not produce the tree, but 4 of these will. Right, so they all start out with 5. That seems like a strong point. Okay. 3, and then the rest do 9. So let's do 3 first. 5, 3, 4. That seems to check out. 9, 12. 9, 12, 7, 8, 6, 20. So that seems fine. 5, 9, 3, 7. Right, and what's going to go wrong if I place one and there's a gap between what I placed, right? So 5, 9, 3, 7, 6, 8, 4, right, we placed 3 earlier. What about 12? 12 is a child of 9, which we've already placed, and 20. Okay, that's fine. What about this one? 5, 9, 7, 8, 6, 12, 20, 3, 4. What about D? 5, 9, 7, 3, 8, 7. So we placed 8. it came after 7. Just double checking there. 12, 8. And then 6, 4. We've already placed 3, so that's good, and 20. So it's got to be E, so let's find out where it goes wrong. 5, 9, 3. So 5, 9, 3, 6. We placed 6 before we placed 7. So that would turn the tree into basically 9, 6, 7, 8. All right, answer 3 of the 4 questions in the space provided. You're welcome to try all 4 problems, but make sure to clearly indicate which 3 problems you want us to grade by circling the numbers of the problem, you sucker. So don't try to grade those. Typically what would happen, although I did take a number of classes, and this gets more common in the upper level, where basically if it's a cross-listed classes, there will be there's typically a requirement that that the courses need to be harder for grad students. So it's typically the way it is that if you're an undergrad student, choose 3 of the 4. If you're a grad student, do all 4. So, Also in grad school, a passing grade is a B or higher. So, in classes, and you're only allowed a certain number of Bs. But for some reason, when you start becoming an expert in stuff, that ends up being a stressor. So, all right. So suppose the the keys on the middle road of a standard keyboard, QWERTY, A, S, D, F, G, H, J, K, L, are inserted into a succession in an initially empty binary search tree. Okay? So the middle row. Draw the tree after the sequence of insertions have been made. And I'm assuming we're just sorting by letters because that makes sense. So let's go ahead. And this will be one of the most unbalanced trees ever, right? So A, S, D, right? F, so comes after D. G, H, G, E, F, G, H, then J, K, L, right? It's pretty unbalanced. Because those actually happen to be in order. I'm not sure that actually I think it might be a myth that QWERTY was designed to slow people down, even though Dvorak is actually, it's supposedly much faster, although the study that was said that says that Dvorak is much faster and more efficient to use, it was published by the military, and the person in charge of the study was a guy by the name of Dvorak, so it's a dubious reference, but actually it's quite efficient. And it's just a matter of first, person who gets adopted has the advantage. Question B, suppose they're in a 2-3 tree. We didn't learn 2-3 trees, so no worries. Skip it over. Hashing. Now something like this will be on the exam. Suppose you are given an initially empty hash table of size 7 that uses open addressing. The following sequence of keys is to be inserted. 15, 7, 8, 23, 3, and 5. Insert these keys using each of the following approaches. If an overflow occurs, say so, and indicate the element that causes the overflow. So we want to insert these keys, okay? And this looks intimidating until you've seen this. Insert the keys, all right? Got something of size 7. And we say the key is going to go at, the hashing algorithm we use is that the key goes to the index x mod 7 resolve collisions using linear probing. Okay? So given a key, we want to place it in x mod 7. So, for instance, 15, so let's go ahead and give me 7 spaces. So 0, 1, 2, 3, 4, 5, 6, and that's already 7. So 0, 1, 2, 3, 4, 5, 6, 7. Wait, that's too many. There we go. Those are our 6 indices. So first we want to insert 15, right? 15 needs to be inserted. What is 15 mod 7? 1. So 15 will go into index 1. Right? Nothing to resolve. There's no collision. 17. What does index that go into? 3. If you're curious as to how to do that, it's pretty simple. Keep subtracting 7 until you can't subtract any more. Right? and that will give you the correct answer for modulo.
So 17 minus 7 is 10. 10 minus 7 is 3. So if we were doing division, we'd care about how many times we could subtract 7, which was 2, but we're doing modulo, so we care about the remainder, which is 3. Okay, so we put it in index 3. 8. What about 8? What index does that go into? 1. Okay, we're going to put 8 in index 1. Except what's going on here? We've got a collision. So what do we do to resolve that collision? Sorry? Next one. So we put it so we put it over here, and it says to indicate with these keys using if overflow occurs, say so, indicate the element that causes collision. I think this is pretty explicit enough to show that causes a collision, right? An arrow over here, right? Just saying, hey, I want to go over here, and 8's now here. Okay. Now insert 23. What's that key? 23 mod 7 is what? 2. 23 mod 7 is 2. Inconveniently, the thing we just inserted. So, okay, we got to resolve this using linear probing. So we go to the next one, which is full. So we go to the next one. So we put 23 over here. Okay, what about 3? That 3 mod 7 goes to 3, which inconveniently is full. And the next one is full, so we put 3 in index 5. Okay? Finally, 5 needs to go into index 5, but that's taken. So we put it into index 6. Right? And we can see basically the path that each of these guys took to get into there. All right. So this is pretty close to what this first example, A, is pretty close to what you'll be given on the exam, because I don't know if the other classes covered quadratic probing. But for practice sake, let's go ahead and see how quadratic probing would still work with this. So it's still the same algorithm over here. Okay? Still the same keys, still the same still the same hashing algorithm, but how would quadratic probing resolve this? Okay. 15 still goes into here, 17 still goes into here. Right? 8 now needs to go into here. First thing 8 does, though, is check the next available spot. So it checks 1 squared away from where it initially tried to enter. Can't find it, so it goes over here. Okay. 23 now needs to insert into what index? 23 now needs to go, 23 mod 7 is 2. So we want to put 23 here. So we now start quadratic probing, which means now we check 1 squared away from where we wanted to go. That's not going to work. So now we check 2 squared away. So 4. So this was 1, 2, 3, 4. So now we put 23 over to here. Right? Because instead of checking 1 away, then 2 away, then 3 away, we're checking next spot, next spot, next spot. We're checking 1 away, 4 away, 9 away. Okay? And yes, you do wrap around if need be. Now we insert 3, which just goes in here. No problem. And then 5 doesn't have to move anything at all. The nice thing about quadratic probing is that it creates more gaps. The disadvantage to using quadratic probing is that it needs a multiplication operation to calculate the indice, as opposed to linear probing where you're just adding 1 continuously. Right? To compute the square, you need to do some multiplication, which is a bit more expensive. And it's not necessarily going to find this first space as quick, right? If you're searching for that last spot, right, and you're just basically hopping over it continuously, it could take a while. Okay. They also had like double hashing, where basically they have a secondary hash function. Notice it doesn't use modulo. That's perfectly fine. But there's no need to go over that, especially since now we want to make sure we have time to do graphing algorithms. Okay. So let's go ahead. So let's see. Let's perform a depth first search, breadth first search, Dijkstra's. Yeah, that's perfect. Okay. So let's take a look at this. Whoops. Let's take a look at this algorithm over here. We've got this graph over here. you know, nothing to write home about, I think, but it's a graph nonetheless. So we want to perform a depth-first search of the graph shown above, starting with vertex C. Okay? Select the smallest edge first when appropriate. So, right, if we're starting from C, right, the first node I could visit, I've got the choice of visiting 2 nodes. I could go to B or F. Oh, and actually I could go to E as well. Right? I've got 3 neighbors. I could select one of them. It's saying that that when there's a choice, I want to go with the one with the smallest edge first. Right? So there will be directions as to how to break tie. It's typically that if you're using a weighted graph, or break ties in select alphabetical order first. Right? We're not going to do something like reverse alphabetical order or using a substitution cipher. Do these first. We're not. It's going to be something simple. Okay. So here we want to list the order in which things are visited. So first we will visit. And I think we can just do this by eye, right? So C we go to first, and we've got 3 neighbors, so we're going to go and visit B next because that's the cheapest, right? 5, 22, 30. So we go to B. B has 4 neighbors, 18, 20, 17, 13. Oh, it also has 5 as well, but we just came from there, right? So that wouldn't make sense if we're, obviously if the algorithm had us choose 5 each time, we'd just be going and swapping back and forth between C and B. That would be no fun. So obviously we don't go back to anything we visited. So from C to B, B to A, that's the cheapest cost. A has 2 neighbors, one of which is already seen, so it goes to D by default. So we've gone C, B, A, D, and now D is a dead end, right? Right? Nowhere else to go. So we back up till we get to a point where we can visit new neighbors. So B has 2 neighbors it's visited, and 2 it's not. The 2 it's not are F and E. So go to F, and F is a dead end, and then E. And then we backtrack, and then we backtrack to C, and we're done. So the answer is we visit C, B, A, D, C bad, and then F, and then E. Does that make sense to everybody? F then E, because F has because we're breaking time. From B, right? We do C bad, right? And then we go backtrack up to B, and then we go to F and then E because those are neighbors of B, right? Okay, so now to do a breadth first. Now we do the same thing, but breadth first, okay? So here, it's just neighbors of neighbors. So C, we visit C first, then we would visit B, and then E, and then F. B, E, F. So now we visit B's neighbors first, which are A and D, and then we visit E's neighbors, which we've already visited. So it would be C, B, E, F, and then A, D. Not really too hard, these. Dijkstra's, on the other hand, I'm going to actually bother going through on the board, right? So here we want to find the shortest path from D, this node over here, to E, this node over here. List in order they become known, all vertices to which a shortest path is determined. You're just going to have a table, so we're just going to do Dijkstra's algorithm as normal, right? And Dijkstra, for all his awesomeness, he was never really. He was a mathematician at heart, so in my opinion, he kind of sucked at naming stuff, right? So we had S, VS, right, and D and P, and it's just much easier if you say, if we keep track of stuff by saying, okay, so we're starting at node D, right? So to do. So with Dijkstra's, we keep track of 4 things. First, the nodes we need to do, which I'll say A, B, C, E, F. Okay. Done we'll handle in a second, but D will be in there. And then we have the list of nodes that we need to find the distances for. A, B, C, D, E, F. We don't really need the distance for D, though, because that's itself. And then we initialize the graph, or initialize this map, or these maps, right? Distance over here, and then the predecessor, okay? So we initialize this, starting from D. What are D's neighbors? These neighbors are 10 and 17, are A and B, which have 10 and 17. And so they have D as the predecessor. And everybody else we don't know how to get to, so their distances are infinity. And they don't have a predecessor. And we don't have a predecessor for them yet. Okay. Oh, that's much better. It costs infinity to get to them from D. Okay? All right. So now the next thing we do is for Dijkstra's algorithm is that we select the node with the next highest cost. So it costs 10 to get to A, so that's the cheapest so far that we know how to get to, and B has a cost of 17. So A is the cheapest that we know how to get so far. So we'll move A from to do to done. And now we use A to see if it's got any cheaper routes. So to get from A to B, that's the new route that we've discovered, that costs 13 plus 10, right? Total, right? Because we'd be going from D to A and then to B. Is that cheaper than what we know? No, so we don't update our graph. Okay, so we're done with A, right? And we can also you can always just move this over as a bunch of check marks over here. So we're done with A. So next, it's infinity, infinity, infinity versus 17. 17 wins. Okay, so B is our next node, and we've got a bunch of new routes over here. So B to C is a cost of 5. So to get to C is a grand total of, well, the cost to get to B plus the cost to get to C, which is 22. So we can get to C for a cost of 22 by going through B, right? It's not 5 here. It's 22 because it's the cost to get to B plus the additional cost to get to C, right? Because now you can ask, okay, it costs 20 to get to C. How do I get to C? Well, you go from B. Well, how do I get to B? You go through D. You go through D first, and it's going to cost you 17 total to get to B. And how do I get to D? You don't need to get to D. That's the starting point. Okay? So now, but that's just the first node we've discovered. What about E? B to E is an edge. So that's 17 plus 20, so that's 37. And B to F is an edge. So that would be 17 plus 18, which is 35. Okay. All right, now we go through and select the next node. So C is a cost of 22, so it's done now. It's got two neighbors that we haven't really looked at. This cost of 22 to E and this cost of 30 to F. So 22 plus 22 is 44, and 35 plus 30 is 65. So those routes aren't any better. Okay. Then for F doesn't give us any new routes. And then E doesn't give us any new routes. So this is the Dijkstra's algorithm. So that's the Dijkstra's algorithm for this graph. All right. Let's see. Okay. Let's go ahead and do some of your coding questions, because half the questions are going to be code and half the questions are going to be theory. It's a 50-50 split for the points. So, and we do favor tree questions, right? So here's one.
Write a Java method named mirror that takes a reference to the root node of a binary tree and creates a new tree with its own nodes that is a mirror image of the original tree. For example, if root is a reference to the root of the tree on the left, then mirror root would be a reference to the root of the tree below. Hint, the method is much easier to write if you use recursion. So it's going to create a new tree with its own node. So it's going to be copying a tree. It's important to know. So it's important to note that. So let's go ahead and start coding that up. Okay. Just going to go ahead and create a new file right here. New Java class, review. Okay. All right. So obviously I'm going to copy this, but I'm going to have to create my own node. I'm going to have to create a node class. Okay. Private static, and I'm just have to create this here because otherwise I'm going to have compilation errors. Private static node, private static class node, and let's just call it int data node. Yeah, I'm not going to bother using generics here. Node left, node right. Okay, so it's got a left node, a right node, and let's just go ahead and say it is a constructor. Public node, giving me an int data, saying, hey, this dot data is equal to data, right? Super. So there's our node, and we really don't need anything else. Okay, let's go ahead and return null over here to quash that error. Okay, so let's think about this first off. Base case, base case, base case. So always think first, what should I return if the root is null? So what is the root? So what is the mirror image of nothing? Nothing. So if root equal null, then return null. Okay. Otherwise, what do I have to do? I have to create a. All right, let's think about this from my perspective. From the perspective of a tree, right? And we may or may not need additional cases, but we'll see, right? Think I'm a node for a second. I've got my left subtree, my right subtree, right? Okay. First thing I need to do is create a node. Since this is going to be a copy, okay, I need to make a new node. So let's call it node evil root, because if it's a mirror image, of course it's evil, right? So evil root is equal to new node root dot data, right? That's all it's going to do. It's just going to copy what's ever in there, right? Okay. Now the next thing I need to do is figure out what I'm going to do with my left subtree and my right subtree. So the answer is I should copy them if they exist. And if they do, then I need to swap them. Okay, so that makes sense. And then at the end, I should return evil root over here. So, okay. So let's go ahead and create a node evil left, node evil right, and let's go ahead and say they're equal to. I'm just going to set them to null explicitly for at first. So if the real root has a left subtree, okay, if that's not equal to null, then if I have a left subtree, then that means that the mirror image will have a right subtree. So evil right will equal to the calling recursion on. Actually, I can just simplify this to say, hey, evil left should be mirror root.left, right? If my left side, not root.left, root.right. So if my right side is null, right, what we'll do, it's going to return null. If it's not null, it'll return a copy of itself. Otherwise, and same with mirror root.left over here. And now we just have to make sure they're attached. So evil root gets dot left is equal to evil left, and evil root dot right is equal to evil right. Hopefully that makes sense to everybody so far. Yeah, on Monday I'm going to be going over a lot more of the coding questions because I wanted this to be more of the theory overview because there was a lot of theory. Okay. So that's actually, I think, all we pretty much need because this will create new nodes for me as needed. Yes?
Would you need those last two steps instead? Couldn't you just return the node root?
Oh, do you mean this?
I
I mean, yeah, I could just put this up. I could just, put this over here and put this over here. But it was helpful for me to figure out the problem-solving process, right? But no, I could make this even shorter. Okay. What is the runtime of mirror? Briefly explain your answer. The runtime is, well, does it hit every node in the tree? So it's O of n, right? Does it do log n operations for each node? No, it does not. It does one operation per node, so it will be, so it's O of n, right? It hits every node in the tree exactly once. And, this exam that we looked at, it was primarily done for, for not much coding. This one over here, right, this is just a implement search, so it doesn't use recursion. How do you do recursion without actually using recursion? You can use a loop, but what data? Yep, you can use a stack. See, so it becomes super easy if you actually use a stack here. So let's go ahead. Yep, so that's good. And what time is it now? It is 11:44. Sorry, 1:44. So I think we're good for today. Since I also see people being quite bored. So Monday is solely going to be just reviewing for your exam. No quizzes or anything. There's no more videos to watch except for, the ones that I said to watch. So congratulations, you've made it to the end of the semester. You've survived. Yay. You're almost there.